morning.
Our homework stuff.
Yeah.
It's brutal. It's very brutal.
Brutal, yeah. He's actually a very kind person, but you would never know it because he tries everything to look intimidating. Very early in his life, but he had to decide to become either English professor, English literature, or physics. And that shows because he writes so exquisitely well. I mean, So today might be a disaster because this morning I decided to improve the lecture. And, whenever that happens, that's a bad sign. So I'll start with the motivational piece, assumption being that, most of us will not be doing 20th century physics. So here is an example. I didn't have a time to get a picture of the monkey, but this is a typical experiment in neuroscience, high-level experiment where you connect, will, cognition, and execution of tasks with a monkey who is basically playing a computer game. So monkey has in front of him joystick, and what he's doing with this joystick, he sees on the screen in front of him certain kind of inputs, so some lights going on here and there, and he has learned that if he moves the joystick to one of the squares that he sees on the screen, he will get the reward, which is a shot of orange juice, which was nice. On a motor cortex, so the region of the brain here that lights up when you have volition to do a task, one implants a small chip with 100 needles which go into the motor cortex, and they measure local voltage at each tip of the needle, and then that set of needles are connected to fine wires which go into the computer. So what you see on the vertical axis here, every entry here is one of the neurons. There are a little bit less. There are over 100 of them in this data plot, I believe. So that's a neuron, that's a measurement that you do, and that's the voltage. And then this is time evolution. And what's being recorded is a spike. Every neuron has dendrites and has an axon, etc. And then every so often when it gets too excited from its input from other dendrites, it fires. And that looks like a spike in a potential. It's something of order of a millisecond. And what's being measured are these spikes. What one does is, it's a binary input. Either you cross a threshold or not. So that's the data for each neuron. One thing one could do is one could just average over all neurons. And what's indicated here is that there is a burst of activity of number of different neurons. Now, we do not know what these neurons are other than they're in the motor cortex. So they have to do with our will to make a motion. We know almost nothing. This is the data. So this is what one has to analyze. Blown up, if you're looking at some number of regions, few hundred neurons around the tip, this is what data looks like, a little piece of data. So it's time versus a neuron. So, these things are as different as bricks and oranges or anything. And we are supposed to, it's talking to us because it's telling a muscle to do something, and we're supposed to understand how it does. Now, here are some results. So the early Nobel Prizes, Hubel and Wiesel in '62, they were looking at activity on the top of a cat's brain. There were some kind of waves going on there. And they realized, so that was visual cortex, they realized when cat sees an edge moving, certain neurons in the visual cortex lit up, and they are direction responsive. So there is a direction which particular neuron, goes very excited, but other directions, as the edge moves in front of cat's eye, doesn't respond at all. And they were even able to measure response to the angle on a given neuron. So that's a single neuron thing. So it sees, that's kind of the input one gets. One gets something from the visual cortex, and it's mapped into activity of a particular neuron. Now here is a more impressive thing. So here, for example, there is a bunch of neurons. These are now different neurons. And this is now done in the motor cortex. It turns out that when monkey moves hand this way or that way, different ones get active. And there are even some that don't get active at all, they're inhibited regions. So for few of these neurons, people could figure out that motor cortex, you can read off which way the hand of the monkey will move. They'll happen about 100 milliseconds later. So you can do this much faster on a computer than the human actually executes the motions. Now here's a really cute example, and that's very much related to what we want. So there are some individual neurons, and it turns out there is a Brad and Jennifer neuron. Some neurons that just go bananas. Well, a particular neuron that goes bananas when the image that a human, now these are the humans, human sees is a particular pair of humans. And it doesn't react very much to individual faces, etc. Doesn't react to beautiful landscape, doesn't react to ants, etc. So it only cares about it. So in your brain, there's a Brad and Jennifer neuron. The reason why we do this to human is we do deep brain stimulation to deal with, first of all, to make them move limbs which have been paralyzed, or move them prosthetic limbs. So if you don't have an arm, but you still have a volition to move your arm, if we can read in moral cortex instruction, move this arm, we can send it to artificial hand and it will do it. And, they're very important, amazing things that people who are totally paralyzed, have this implanted, and they can move by thinking the cursor on the screen and, type messages and stuff like that. So you get trained. So this is, much more important than most of physics. Totally amazing. And this is a stupid illustration of kind of data that we look at. So that's in a way of motivation. Here is the old stuff. I started explaining that physicists tend to think of matrices the way they show up for Newton, which is solving differential equation, evolution, and time. They're very important. Turns out sometimes cannot be diagonalized. So our eigenvectors and eigenvalues, sometimes you get deep trouble. But in data science, you have to do something totally different. You have, for example, I showed you a space of faces and non-faces. So that's one axis. Or in measurements in turbulence, you have a video. So you have different snapshots of three-dimensional fluid, which human cannot visualize, but you can put it as data in. And this could be time, and this would be the features space. And when you have this, we saw that, for example, there were regions of high activity. So in these data sets, there are important parts and there are lots of unimportant parts. They could be, 1,000 times smaller entries in a table, so you can neglect them. Or your measurements could have noise, so you don't take seriously anything whose magnitude is less than your noise, let's say 1% of the typical entry, but you get focused very much on entries in this data set which are of order 1 or large. So that's a totally different use. And because it's so important, I will give you a miserable little lecture, but I'm giving you links to some beautiful lectures on the web, which are done, amazingly well. Also videos, but really good. So, it's a typical kind of matrix problem. You would like to solve you have some input, some data, you're incredibly lucky and linear methods work. And that's one of the amazing things about lots of this neuroscience work. Things that physicists think are totally wrong because they're linear. Nothing is linear in this world. They manage, for deep reasons we often don't understand, to look at the data, do something to it, and get a response. So for example, this is a vector of I want to move my hand, and this is a vector of, I saw Brad and Pitt. So you have to solve this. And something that they knew from the very beginning, nobody says that this matrix has to be square. And why is that? You can measure as many time pictures or faces as you want, and you can count so many features. They have nose, don't have nose. So typically these are very non-rectangular, non-square, very rectangular data sets. And we have to invert this thing, but we know how to invert square matrices with determinant is not 0, but these are not square matrices. So what does it even mean to invert them? How do you do this? And then what we want to do is we want to order our result in some way in which the most important things is what we'll look at first. So in that particular thing with lots of faces, the first 6 were Brad and Pitt because those are very large numbers in the data set, and the rest are small. So you want to extract the important features. And the original intuition came from, at that time, since 18th century, we had complex numbers, so, real part plus imaginary part of a number. So in 1850s, these people knew that there are 2 ways of writing a complex number. One was to write, you take z and you write it as x plus I, y. That's kind of Cartesian way because you can draw this on a real imaginary plot. But then they also knew that you could write r e to the I phi, which is a polar representation. So this is a 2-dimensional matrix when you act on a complex number, if you multiply with something. And if you do it in polar way, then what it means is, you have to change your coordinates in such a way that you extract the length. And there is an angle. And in Professor Zangel's course, if you get that far, there'll be waves, electromagnetic waves at some point. And, we care about R being large and maybe not so much about the phase. So if we square this number, that in electrical engineering is called the power, how much do I burn? So they knew that this was the thing to do, and they felt that they should be able to do this also for other matrices, not just 2x2 matrices, which is representation of complex numbers. That we'll do in 2 weeks from now. And they knew continuum physics. They knew how to stretch materials, etc. And they had this picture that, the way you deform something is that you can rotate, you can deform, and you can back. And that gave them a first hint how to write this thing that was called a polar decomposition. I gave you a link in lecture notes to it, but you don't have to read it. And so that kind of method is today called PCA, and I'm writing this because you might run into all these acronyms because it's a little bit like Soviet Union, everything engineers write this acronym. This is called principal component. Now, this lecture notes are based on a Twitter feed because in neuroscience, Twitter is very important. They really communicate on Twitter. So I took down a whole overly excited Twitter feed by a brilliant statistician called Daniela Witten. And she explains that everything anybody else tells you is a special case of what we're doing now. And that is called singular value decomposition. So that's what I'll try to explain. It doesn't have to be data. It's just linear algebra, but I'm coaching in this language because you're most likely to do this in your lab by looking at data. Data is presented to us as a matrix, and when you get fancier, you might not look at matrices, you might look at tensors, which means there are data arrays which have more than 2 indices. Matrix has 2 indexes. So, the modern stuff is today tensor and this and that. But for purposes of this lecture, we have a data matrix. And data matrix is organized. There is a column vector 1, column vector 2, and there is a column vector n. And I'll do the horrible thing. I'll be interchanging m's and n's, and you will kill me, but here we are. So you produce data matrix from stack of individual measurements, and they're typically some pixelized things, so you can rearrange a square photograph into a bunch of columns on top of each other, so that's always presented as a vector. And now these xi's, we'll assume they're real number, and this will be, it's gonna be the disaster. For purposes of this lecture, it's not important, but it's mathematics, but mentally it's important. N is larger or equal to m. So kind of square matrices that we study in physics often is a special case of this. So you can do this also on all the matrices we have discussed before in this course. So that's our data. Here is the statement, which is not obvious. And the first part of it comes from 19th century. It says that no matter what this matrix is, I can think of it in the following way. I can do rotation, which rotates along the feature space. So this is rotation matrix. And this is rotation matrix that doesn't change length. This is really rotation. So this is how they thought of stretches in continuum mechanics. You know, you go to coordinates where you stretch, then you stretch, you experience stress, you record it, and then you go back. So that's a step number one. Now, if you're cleverly chosen this rotation, you'll get into the natural coordinates. So this matrix is orthogonal or unitary. You know, if we are looking at complex numbers. If there's a complex arrays, then we call it unitary. Then there is a matrix which is diagonal, and this is we have rotated into natural coordinates for particular deformation of our data. So this one really describes axis of an ellipsoid. It says in this direction I stretch by that much, and in this direction I squash by this much. So that's what this matrix does. And then I have to rotate back. So this is also orthogonal or unitary. Now this is a cookbook recipe. You know, what's a cookbook about it? We demand that this matrix, sigma, and here, this matrix operates in a space of feature. It mixes it up. So this is just n by n matrix. Now this has to have the same, you know, dimension as this huge orthogonal matrix. I mean rectangular matrix. So this is n by n. So this guy has to connect somehow 3 dimensions to 10,000 dimensions, you know, depending what they are. So this has to be rectangular of the same size as the guy here. So this diagonal matrix says elements on diagonal as many as, you know, I can distinguish in my feature space, zeros off diagonal. And, you know, I padded with zeros all the way, all turtles down to make it of this same size, n cross n. But morally, the only thing that matters is this diagonal part. And then one says, let's order this one. So the first number of diagonal is larger or equal to the second. They can be same value, they can be degenerate. It goes to this guy, which is strictly larger than 0. Because if it's 0, you know, it has no effect. So these are positive numbers. This is a non-negative diagonal matrix. And just that leads to unique decomposition, which is not obvious. So 2 amazing claims, you know, SVD, this writing as a product of 2 rotations sandwiching a diagonal matrix, is 1, unique, and 2, every matrix Because it's so important, any decent programming language has a command called singular value decomposition, or SVD, and you can stick in whatever matrix you have, and it'll give you these three matrices. This means transpose, meaning that if V was 1, 1, 0, 1, then V transpose flips everything across the diagonal, doesn't change the diagonal. And this is, defined to be transposed for convenience, but the basic property of these two matrices is that the inverse of each one is just a transpose. That's a basic thing about rotation. If you don't remember it, we'll get to it in the course later because these rotations are very important to us. So this is a matrix of size M. This is a matrix of size Mn. So this is huge, this is little. And then it's easy to show that it's also true for VV transpose. You can multiply them in either way, give you identity. We are only allowed to use rotations for the outer matrices. And the other ingredient that we use is that the values are all ordered. And then miracle happens. There's a unique way to always do this. And then there are, words. I have no idea why is this called singular, but these things are called singular values. And then U and V can be written as columns. So these guys are called left singular. These are big guys. And then there is a V, which is much smaller, also has columns. These are called right. And I beg you, never confuse eigenvectors and eigenvalues with singular vectors and singular values. Even for 2x2 matrix, they have no relation. It's very complicated to go from one to the other. They're totally different beasts. But there is infinite confusion in people who, do specialized subjects like fluid dynamics or neuroscience, mixing up eigenvectors and eigenvalues with singular vectors and singular values. Here we are. We have U, sigma, three matrices, E, T. This code is built from right eigenvector, singular vectors. And these are singular values. And what's the big deal? You were given some incoherent set of neuronal recordings. Now, once you get this matrix, then it has a first column, which is multiplied by the first number, which is the largest singular value. In this matrix. So the eigenvector U1 is the most important. because we give it most weight. Then the second one is next most important. So if you're doing Google rank and your matrix is billions by billions, it is very important to find the most important column. So you reorganize your data in a way which is totally different. But now, this says which kind of series is the most, let's say time series is most important, and which kind of phase on the right-hand side or which kind of twirl in a turbulent fluid is most important. So that's why this is so beloved by our colleagues.
By most important, do you mean the largest eigenvalue?
See, you did it. I would like to have 5 cents every time everybody in the class does this. Singular value. It's not eigenvalue. Singular value. Totally different, yeah. Never mix up the two. But other than that, you're correct. It says that, yeah.
Would it be possible to go through an example of how they're different? Maybe not today, or do you know of like a good resource to go see how they're different?
I gave you that example, but I didn't show you a number. When I showed you the picture of Brad and Jennifer, they were now organized. They belong to the most important column. So they showed up at the beginning of our data set. Usually you're given 1 million pictures and they're all random, right? Take them 1, 1, 1, 1. Once you're finished, the Brad and Pitt all show up in the first 4 columns. And then there are other pictures. So, I showed you an example. Now, what we might do, but I'll make you do it by hand because it's very, unless you do these problems by hand, it'll be just some stupid routine in the computer. So we will do it, but my goal here is to explain the intuition behind it. So there is one thing that everybody who looks at data, one needs to know about correlations. The way that this is implemented with giving this data is you look at your data set, which is a rectangular matrix, and you multiply it by its transpose. Which is, if your X was, a long skinny thing here, you have multiplied it by its transpose. And the result is a small matrix. And what's inside of this matrix? Now remember what these things are. They are vectors of data, for example. So then what I get is in here, in the first time I get X transpose 1 times X, by multiplying first column with the first row, and on X transpose 1. So these are vector products, right? Where, X transpose times X. This is a sum over this guy has elements. Let's label them K. Every one of them is entry of products of the two of these vectors. And that's called correlation matrix. Now, even though our data was a huge incoherence thing, correlation matrix is very nice because it's obviously symmetric. Because, this is just a number. The transpose of this number is 10. So this equals that. There's stuff on diagonal. And it's a nice matrix, and it's actually a matrix that we studied on Tuesday when we were studying normal modes. It's a symmetric matrix which is bilinear in our data fields, x's, whatever they are. And symmetric matrices are great because they can all be diagonalized. And, if I don't have a non-zero part of this, I might even they have strictly positive eigenvalues and non-negative, and so on. So they are great. And the way we visualize them, we compute the eigenvalues and eigenvectors of a symmetric matrix. We can use these eigenvectors to rotate to the intrinsic natural frame. For symmetric matrices, and now we are talking eigenvalues and eigenvectors and not singular values, singular eigenvalues. We can rotate, and that's what V matrix does, to orthogonal frame, which has eigenvectors of this symmetric matrix or organizing intrinsic directions. And the most important direction is multiplied, it'll turn out by singular value squared. That'll be the length of ellipse in this direction. Then the next important will be the second one, sigma 2, etc. What this does, and that's what we often do with our data, we say we have some kind of cloud of data in high dimension. Now, can we find the most important direction along which the data is arrayed? That'll be the first semi-axis of an ellipsoid. Then we rotate our coordinates, so our data is arranged that way. Then we do this for the second, third, fourth coordinate. And if you're lucky, we find out that the first three sigmas are big, but fifth or sixth sigmas are very small, which is now a step in dimensional reduction of our data. We have now reorganized our data in a way such that we see the most important part first. Explain this in a little more detail. So the essence of the whole singular value decomposition is to treat the data we are given in terms of its second order correlations. And why do we speak of correlations? If these eigenvectors are faces, so I have different faces, then if I see the same face, then this correlation number will be big. But if one of these vectors has to do with the face and other one with the sandy beach in Tahiti, then when we dot those two images, we'll get a small number. So that's the intuition, why we are looking at correlations. This is the first thing we can do when we have data. We can compare it, and we can try to find the important regions this way. Data was U sigma bt. Then the transpose of our data is the transpose of these three matrices. So it's V sigma transpose times U transpose. But remember, morally, this is a diagonal matrix. Sigma T. Diagonal matrix, nothing changes where you transpose it, so this guy didn't change. Now we can compute xt times this transpose. And that is V sigma, well, not transpose here, U transpose times U sigma V transpose. Now these two guys, this is unitary or orthogonal matrix, so that's 1. So we get that this transpose is sigma square, the diagonal matrix. So this is some symmetric matrix, and it's been brought up to diagonal form by rotation V transpose at its inverse, and its values in diagonal form are the singular values. Now I can multiply both sides by V, this matrix multiplied by matrix V equals matrix V sigma. And what do you know? You know, if I write V as V1, V2, then this is actually just an eigenvalue condition. It says that X dx, this correlation I will be. So it turns out the singular values and singular vectors are related to eigenvalues and eigenvectors, but in a weird way. So we have to look not at our original data, but the correlation matrix built from the data. That's a symmetric matrix. It has eigenvectors, Vi, and it has eigenvalues as squares, singular values. And you know, it had to be that dimensionally because X is in decomposition are linearly proportional to the singular values. So if I take a bilinear combination, it'll have to happen. So now we have an interpretation of what this is. You know, this is a rotation given by this correlation matrix in a feature space. Now you can do the same calculation if you do the same calculation for X times X transpose in the other order. It's identical, but you'll find out that now you have, this is a big matrix. Because remember, X is rectangular, so this is the direction in which it's big. It will lead to the transpose equation for U but with the same eigenvalue. This is actually now how we proceed to compute these guys. You give me your data. I make the little matrix out of the data. So for example, there are 100 neurons, so I work in a neuron space. And I find the way we have already done this in the preceding part of the course, eigenvectors and eigenvalues. This is a non-negative matrix, and these are squares of singular eigenvalues. This rectangular matrix, that's given, we have it. Gymnastics. And that gives us, in the usual way, set of eigenvalues, singular values, as square roots of the eigenvalues of correlation matrix. And we have the matrix V, remember we are looking at XU sigma VT, we have V whose columns are the eigenvectors we just computed. So the only thing I don't have are these U's. So I multiply from this side, so I multiply X by V. That gives me U sigma. Now I multiply by this matrix, sigma minus 1. That gives me U. And that always works.